Hello everyone. Have you ever watched a cricket match on TV and noticed the run rate graph shown after each over? It's an instant way to understand how the game is progressing. In physics, we use graphs in the same way to represent motion visually. Graphs make motion easier to analyze because they show relationships between two quantities like distance and time or velocity and time. With just a glance, we can tell whether the motion is steady, speeding up, or slowing down. So today, we'll dive into how graphs reveal the story of motion. Let's begin with a simple case, uniform motion. Imagine a car moving at a steady speed. Every equal interval of time, it covers equal distance. On a distance-time graph, with time on the x-axis and distance on the y-axis, this shows up as a straight line. The slope of this line tells us the speed. Mathematically, speed equals open bracket s to minus s1 close bracket divided by open bracket t to minus t1. So, a steeper line means the car is moving faster, while a gentler line means slower. But what if the car doesn't move steadily? Suppose it slows down or speeds up irregularly. The distance-time graph no longer gives a straight line, instead, it curves. For non-uniform motion, the slope keeps changing. To find the speed at a particular instant, we draw a tangent to the curve and calculate its slope. That gives us the instantaneous speed. This is how Fig. In your book shows a car's motion with varying speed. Now let's move to velocity-time graphs. Here, time is along the x-axis and velocity along the y-axis. If an object moves with constant velocity, the graph is a straight line parallel to the x-axis. The height of this line shows the velocity. And here's something powerful, the area under the line gives the displacement in that time interval. For example, if a car moves with a constant velocity of 40 km per hour, the area under the graph gives the distance it has traveled. Things get more interesting when the object accelerates uniformly. Imagine a car steadily increasing its velocity. On a velocity-time graph, this appears as a straight sloping line. To calculate displacement, we find the area under the line, which forms a trapezium. We break it into a rectangle and a triangle. Then add the two areas to get the total displacement. Mathematically, S equals AB multiplied by BC plus half of open bracket AD multiplied by D close bracket. So the slope of the line gives acceleration and the area under it gives displacement, two insights from one graph. Finally, if the acceleration is not uniform, the velocity-time graph can take irregular shapes. For example, Fig. A shows a straight line sloping downwards, that's uniform deceleration, velocity decreasing steadily. Fig. B shows a zigzag line, velocity changing unevenly, first up, then down. In such cases, instantaneous acceleration is obtained by looking at the slope at a specific point on the curve. Let's work through a solved example. Suppose a car starts with uniform acceleration as shown in Fig. The velocity-time graph forms a trapezium. To calculate displacement, we find the area under the graph. We split it into a rectangle ABCD and a triangle ADE. So, S equals AB multiplied by BC plus half of open bracket AD multiplied by D close bracket. This gives the exact distance traveled by the car in that time. The key exam tip: always divide complex graph shapes into simple ones like rectangles and triangles to calculate areas. So, let's wrap up. Distance-time graphs tell us about speed, slope equals speed. A straight line means uniform motion, while a curve means non-uniform. Velocity-time graphs tell us about acceleration, slope equals acceleration, and area under the line equals displacement. Uniform acceleration gives us neat straight-line graphs, while non-uniform acceleration gives curves or zigzags. Graphs are powerful because they turn motion into something visual and measurable. With this, you've learned one of the most useful tools in physics. Next, we'll take these ideas further into the equations of motion. Until then, keep practicing graph problems, they're exam favorites. See you in the next session.